Biostat 66111. Skills for the rest of your life. Bootstraps and probability. It's the bread and butter, baby. What's your jam?
Greetings, Bios 6611. In this final installment of deriving formulas and relationships for simple linear regression, we're going to look at the relationship between the coefficient of determination, r squared, and that measure of linear correlation, or Pearson's correlation, r. In simple linear regression, we know that the square root of r squared is equivalent or equal to the correlation coefficient between x and y. Or another way of thinking about it, the square of the correlation coefficient is equivalent to r squared. We're going to work through this on the whiteboard, but we're going to get started here with a few notes before switching over. We can recall from the introduction of r squared in one of our past lectures that it's equal to the ratio of the sums of square of our model divided by the total sums of squares. This is written out in our notation in the context of regression in our numerator as the sum from I equals 1 to our nth observation of the predicted value y hat I minus the mean of y squared, divided by, and then our denominator, the sums of square total, the sums from I equal 1 to n of yi minus the mean squared. What we can do there is we can take our y hat I and we can plug that in here to our equation to work with a little more on the whiteboard. So let's take a second to pause and switch over to our whiteboard. Okay, now that we've switched over to the whiteboard, we can work on showing that r squared in the case of simple linear regression is equivalent to the square of our Pearson linear correlation. The first thing that would be helpful to potentially do is to replace beta naught hat with our simple summary equation y bar minus beta hat 1 times x bar. And so if we do that, we'll just see that we have a slight rewriting of our formula here where we will have y bar minus beta hat 1 x bar plus beta hat 1 xi minus y bar all squared, then divided by the sum of I equals 1 to n yi minus y bar squared, our sums of square total. The next thing we can do from here is that we can note that we actually have a few terms that potentially can cancel out with each other. For example, we have y bar minus y bar there, so we can imagine that both of those get canceled out. Another thing we can note as well is that in this case, beta hat 1 is a constant. It's some term we've solved for. So for each one of these, we could factor those out and pull them out in front of our summation symbol there. So what we see here is if we do that, we can, I guess, maybe not skip all those steps right away. We'll start with I equals 1 to n. That'll be then the sum of beta hat 1 of x bar, negative x bar plus xi, all of that squared, divided by the sum of I equals 1 to n yi minus y bar squared. What we can then do here is we can note that again, beta hat 1 is a constant term here on its own, and we can also note that it's currently being squared, so if we factor it out, we'll note that it's really beta hat 1 squared times the summation from I equals 1 to n. In this case, we'll reverse the order of our x's to make the negative symbol come a little more naturally to be xi minus x bar. That'll then just be squared itself, divided by the sum I equals 1 to n yi minus y bar squared. At this point, we're going to scroll down a bit here to give us some more room to work with. Now at this stage, since we have beta 1 hat squared on its own, what we could do is we can replace that with the actual equation we solved for from our summary formula. So we see here in our next line of our equation, we can have then that representation I equals 1 to n, xi minus x bar times yi minus y bar divided by the sum of I equals 1 up to n of our xi minus x bar squared. And of course here it's all squared because we note that that's what we have here for our term of beta hat 1 squared. We'll then just multiply that by the sum of I equals 1 to n xi minus x bar squared, and then the sum of I equals 1 to n of yi minus y bar squared. At this stage, we can note that we have a few terms that we could cancel out. For example, we have our similar terms here of the sum of I equals 1 to n, xi minus x bar squared. The one thing we want to note here, though, is that we do have that squared term that's included there for our first term there in the denominator. And so if we scroll down a little bit here to give us, again, a little more room to work with, what we could do is we can rewrite this term here, though, taking that into account, where we can say we have the sum of our xi minus x bar times yi minus y bar, and we'll take that squared divided by the sum of I equals 1 to n of xi minus x bar squared, again taking into account the fact that we have those two terms we boxed in red above, and they're canceling out part of those terms there. And we can also note then that what we really have as well is just in our denominator here, it'll also be times then yi minus y bar squared. So at this point, what we have is pretty close to our representation of the Pearson correlation coefficient. So at this stage, we're pretty close to getting the format we'd like to see. So just for reference, we're going to write down right below here what we're trying to solve for, that r can be shown to be calculated or equal to xi minus x bar times yi minus y bar divided by the square root of the sum of our xi minus x bar squared times the sum of yi minus y bar squared. And so this is our sort of brief interlude here to represent that we're almost there. We see a lot of our pieces there together. And what we can note is that if we give ourselves a little more room here, if our next line is written right below here to see if we can get it equal to what we have above, what we can note is if we take out that square term and we actually rewrite what we have here, we can say that we have the sum of our xi minus x bar, yi minus y bar, divided by the square root of the sum of our xi minus x bar squared times the sum of our yi minus y bar squared, and all of that will then be squared, which we then see will match what we're trying to show to be equal to as our Pearson correlation coefficient squared. So there, with a little manipulation and a little work of rearranging the terms and putting them in a different way, we're able to demonstrate that r squared is equal to r squared for our lowercase r for Pearson correlation. So in brief conclusion, what are some implications or things to take away from this, and what does it imply? Well, the first is that there's really just a lot of interconnectedness between the various concepts, summary statistics, and quantities that we've looked at that may be apparent at first glance. And I think that's especially true seeing how much manipulation we did throughout these three sets of different derivation lecture videos. The second thing to note, though, that might be more practically useful is if we were only interested in a quick takeaway on this simple linear regression case with one predictor variable of how much variation x may be able to explain in our outcome y, well, what we could really do is calculate the Pearson correlation coefficient and square its value. And that may be more efficient and straightforward than having to conduct a handful or a bunch of different simple linear regressions and then trying to pull out the coefficient of determination or get all those other summaries at the time we just may not be as interested in. So there we have it. Two takeaways about the crazy interconnectedness between these various quantities, but also a quick shortcut that if you're interested in summarizing a bunch of these things on this unadjusted simple linear regression case, you may be able to just do the Pearson correlation and use that squared to get an initial idea of the potential amount of variability explained.